Hey everybody, here for the last three problems, or four problems, no, 3, 6, 7, and 8, although I mean each problem has like 2 or 3 parts for Gravner's practice final. Apologies for the poor video quality on the other video, and hopefully not, but probably this video as well. I don't know why the video quality is so blurry. I can see it's on YouTube in 720p. I've recorded it in HD. I don't know why. Usually when I upload to YouTube, it does eventually get to HD. So maybe it's just taking its sweet time. Maybe there's less bandwidth on the weekend. I don't actually know. So again, apologies for the poor video quality. Hopefully the description or the words I'm saying at least will help you understand what's happening. And you can also look at the solutions that are posted from Gravner, and also I will post what I've written up as well, so you can look at what I've written. But yeah, sorry about that. Let's look at problem 6. So this one we actually did this one in class. You can see the video of me doing it from class on Thursday as well. Let me go through this one kind of quick since we already did it. So we've got, I do want to point out one difference between the way I would solve this and the way that Gravner is solving this on the solutions. So you've got a runner running a straight line on a trail of like 7 miles. The trail goes from point A to point B. We're saying that this distance here is 7 miles. And then the person has gone some distance X. We'll say like this distance here is X. Yeah, let's say. So that distance is X. This distance here, which you're going to use later, is going to be 7 minus X. I have to add the 7. And then we're given that point Q over here is 4 miles from B. And point P over here is 3 miles from A. And nicely that you're given this picture and the problem, you don't have to actually draw it out. And then we're asked questions about how far this distance and this distance are changing, which he has labeled as S and R. So here's how the first question reads. At some time, the distance between the runner and A is 4 miles. Sorry, so we're talking about when X is 4. So again, we're not going to plug in 4 just yet, but this is part A. So when X equals 4 miles, the question being asked is, sorry. Oh, well, actually, we're giving more. So apologies. When X is 4 miles, at the same moment, the distance between the runner and P, so that means the distance between the runner and P, which we're calling R, when X is 4 miles, we know that that distance, R, is changing at a rate of 8 miles per hour. It's increasing 8 miles per hour, so we're going to say that dr dt is 8 miles per hour. That's what it means that R is changing at 8 miles per hour. What else are we given here? And then we're asked to find how fast the runner is running. So we're given this when X is 4 miles, and we want to find dx dt. We're going to set an equation relating, hopefully, as few variables as possible. So typically, we would like an equation that just involves the thing that we want to know and the thing that we're told. So we want to know how X is changing. We're told how R is changing. So ideally, I would use this triangle to say, using the Pythagorean theorem, that X squared plus 3 squared equals R squared. Now here's the difference. Gravner then says R equals the square root of X squared plus 9 and differentiates both sides there. And says like dr dt equals 1/2 X squared plus 9 to the negative 1/2 times 2X times dx dt, which is fine, but to me feels like kind of defeating the purpose of doing this in a nicer way. So a nicer way to do this is, instead of this and then plugging in whatever, you differentiate right away. You don't solve for R. You don't need to solve for R. So the derivative here is going to be, well, left side 2x dx dt. Derivative of 9 is 0. Derivative of R squared is 2R times dr dt. Plug in what you know. So I know that X is 4 miles. I'm trying to find dx dt. I know, actually, I don't know what R is. I'm going to use this equation here and then plug in X equal to 4 and say that 4 squared plus 3 squared equals R squared. So R is going to be 5 because it's the square root of 25, which is 5. And then dr dt was given to be 8 miles per hour. I don't really need the units there. I'll plug them in the end. I would point out that the 8 here and the 8 here can cancel. So or divide both sides by 8, and those will divide out. So dx dt is just going to be 2 times 5, which is 10 miles per hour. right? Because 2 times 5 times 8 divided by 8, the 8's cancel. Cool. The other part of this, similar, right? So part B, which I think we can squeeze in down here. So part B is asking the same question, or I should say at the same moment, again, when x equals 4 miles, now we're asking how the distance between x and p, or the runner in q is changing. We've called that s, so we're asking how is s changing, or what is ds dt? So same idea, we're going to get an equation involving preferably just x and s. So I'm going to say that this squared plus this squared equals that squared. So I've got 7 minus x squared plus 4 squared equal to s squared. Again, no real need here to solve for x or for s. Just differentiate both sides as is. The derivative of something squared is 2 times my something times the derivative of the inside. The derivative of negative x is negative 1 times dx dt. So I know I keep looking down because I keep seeing like my picture down there. I guess I can move it up. Kind of distracting to me. Let me move my picture here. Right, one second. So I just don't look like I'm looking at the there. Now I can look like I'm looking at the camera. Great. Awesome. So you have 2 times 7 minus x to the first times negative 1 times dx dt plus 0 equal to 2 times s times ds dt. Again, we're going to plug in what we know. We know that x is 4. We just found dx dt in the previous problem. It was 10 miles per hour. Negative 10. And then finally on the right hand side, you have 2 times s, which we need to find. So we had to find x last time, or sorry, r last time. So if I plug in 4 for x, I'm going to get right here 7 minus 4. So 3 squared plus 4 squared equals s squared. And once again, you're going to get a value of 5. I'm sure this was thought out well ahead of time to make sure the numbers came out nicely. So we're going to plug in 5 for s. Be careful, that's s there. This is 5 here. And then simplifying here, that's a 7 minus 4. Divide both sides by 2. So you have 3 times negative 10 is negative 30. And then divided by 5 is negative 6 miles per hour. So what that means, you could say that ds dt is negative 6 miles per hour, or you could write the ds dt, you could write the s is decreasing at 6 miles per hour. Either way. I would probably just write ds dt equals negative 6 miles per hour. But it does make sense, right? If our runner is moving up this way, it makes sense that s is decreasing in length. Let's look at problem 7, which looks like a graphing problem. So let's see here. Throughout this problem, the function f is given by f of x equal to 1 plus 4x squared divided by x squared, which is also equal to x to the negative second plus 4. And I would also imagine it as 1 over x squared plus 4. Again, we are given that the domain is x being purely positive, which is not the natural domain for this function, but it probably is going to make some of the sign chart stuff less weird. We're not going to have to worry about the sign changing when x is equal to 0 because it's a vertical asymptote. We are going to get a vertical asymptote at 0. Yeah, we're going to get a vertical asymptote. Yeah, we get a vertical asymptote there. So part A says, identify the monotonicity and concavity properties of the function, compute the relevant limits, and sketch the graph of f. Okay, so to me, that feels like it's missing a few things, but all right. So first, monotonicity just means where is it increasing, where is it decreasing? So take the derivative. I would use this version of it, take the derivative and write it as negative 2x to the negative third. I would rewrite it as negative 2 over x cubed. And then since I'm only living in the 0 to infinity region here, right? 0 is my left endpoint because my domain starts at 0. I can see that for any value of x, I'm going to get a negative derivative. So my derivative is going to be negative everywhere, which means my function is decreasing everywhere. There's no other option. If this had been defined on the entire domain, we would have seen that the derivative was negative over here and positive over here. So it would have been increasing, decreasing. We would not have had a relative max. We would have had a vertical asymptote where it's going to go, up on the left and down on the right. That's, I think, all there really is to say. So I'll point out that this is, so I should say that f prime of x equal to negative 2 over x cubed is always less than 0 for x being positive, because we're stuck with x being positive. And then for the second derivative stuff, f double prime of x, I'm going to get, well, the derivative, I would look at this negative 2x to the negative third. The derivative there is 6x to the negative fourth. I'm going to rewrite that as 6 over x to the fourth. And I'm going to observe that actually it wouldn't matter if it was x was positive or negative. This is always positive for any value of x that's not 0. Which means on my second derivative sign chart, second derivative is always positive, meaning the original function is concave up. Okay, what else? They ask us to compute the relevant limits. So to me, that's the limit as x approaches 0 from the right, because we're defined to the right as 0, and as x approaches infinity. So if I look at the limit as x approaches 0 from the right-hand side, it's probably easiest to look at this version of it, to be honest. Either one, actually. You could do either one. So of 1 plus 4x squared, I'll do the original version. If I plug in 0, I get 1 over a small positive number, which is going to give you a positive infinity. No big surprise there. And then if I do the limit as x approaches infinity of 1 plus 4x squared over x squared, it might actually be nicer to look at it as the limit as x goes to infinity of 1 over x squared plus 4, because then it's obvious that this part goes to 0 and you're left with 0 plus 4. You could also pretty easily see it's going to be 4 here, because we know that we have a rational function where the degree on top and the degree on the bottom is the same. So the limit's just 4 over 1, which is 4. So we have a horizontal asymptote at y equal to 4. Then we're asked to graph it. The graph is pretty kind of basic because there's not a lot going on. Here's your x-axis, here's your y-axis. Here's my horizontal asymptote of y equal to 4. There's no relative extrema, there's no inflection points, there's no intercepts, because you don't ever get to set x equals 0. So it just kind of looks like this. Kind of unexciting. It's definitely concave up, because any tangent line I could draw would be underneath the graph. It's also certainly decreasing because you're going down from left to right. Cool. Let's look at question B. Still the same function. What is the smallest possible area of the triangle formed in the first quadrant by the x-axis, y-axis, and a tangent to the graph of f? That's a good question. I'm a fan of this question. Let's just draw ourselves a little tangent of f. So let's say right here. Now, the whole point of this problem is we don't know what this point of tangency is. So we're going to label it a comma f of a. Usually you want to avoid using x comma f of x here, because we kind of use x already. So don't confuse yourself here. Definitely pick a different line. So I want to find the area of this triangle. So I need to find the base and the height. So interesting. Okay, so let's think about what we need to do here. So using this triangle. Yeah, so I really actually do need to think about what am I doing here. I could look at the solutions, but okay. So I guess we should probably find the equation of this tangent line so we can find the x-intercept and the y-intercept. Because here's what I would say. So let's pretend like for a second, the x, let's just go, yeah, sure. So I can think of the area of the triangle as being, well, the area of the triangle is 1/2 base times height. And literally the base is just the x-intercept. The height is just the y-intercept. So yeah, finding the equation, it's a sneaky problem. It's asking you to find the equation of the tangent line without asking to find the equation of the tangent line. So let's find the equation of the tangent line, and then we will find the x-intercept and the y-intercept in terms of a. All right, so here's my line, and I know how to find the equation of the line. It's y minus the y coordinate equal to the slope, which is the derivative, times x minus the x coordinate. This is the reason right here why I don't want to use x instead of a. I want to use a because I'm kind of already using x in a different context. I'm plugging what we know. So I know that f of a. So again, I'm plugging into this function. Remind everybody that f of x is 1 over x squared plus 4, which might not be the best way to write it, but that's how I'm choosing to write it at this moment. So f of a is going to be 1 over a squared plus 4. Similarly, f prime of x is -2 over x cubed, so f prime of a is -2 over a cubed. We might switch things around as far as how they're written. So let's see. If I plug in here, I've got y minus 1 over a squared plus 4. That's not how he's doing it. It's fine. Equal to -2 over a cubed times x minus a. And now I'm going to try and find both the x-intercept and the y-intercept. So I don't think you actually need to solve for y here, but we certainly could. If I do solve for y, I get y equal to, I'm going to distribute that We get -2 over a cubed times x. -2 over a cubed times negative a is +2 over a squared because one of those a's cancels. Interesting that he did. Okay, and then I see. And I'm going to add the 1 over a squared and the +4. And I will point out that this 2 over a squared plus 3 over a squared, 2 over a squared plus 1 over a squared does become 3 over a squared. So then, find the y-intercept, set x equal to 0. Y is going to equal 0 plus 3 over a squared plus 4. That's my y-intercept. I'm gonna write as 4 plus 3 over a squared. Y-intercept, and then my x-intercept, I'm set y equal to 0. It's a little bit more work to find the x-intercept. So setting this equal to 0, I've got 0 equal to -2 over a cubed x plus 3 over a squared plus 4. I'm going to bring that over there and get 2 over +2 over a cubed times x equal to 3 over a squared plus 4. I'm going to multiply everything by a cubed to get 2x equal to 3 over a squared times a cubed is 3a. 4 times a cubed is exactly that. And then divide everything by 2 to get x equal to 3/2 a plus 2a cubed. And yeah, that's pretty much, I mean, he did factor out an a. Okay, that's fine. It's close enough. So then plugging those into this equation here, our area is going to equal 1/2 times the base, which is the x-intercept, times the height, which is the y-intercept. And I would definitely recommend multiplying this out before I try to take the derivative. So multiply it out, and wow, he multiplies that and it looks real nice. So let's multiply. Wow, that does look really, his looks way better than mine. I'm not gonna lie, his looks a lot better than mine looks. So I suppose I could have done some simplifying here if yeah, oosh. Yeah, so I'll point out if I multiply this, yeah, sorry, I'm like this, I'm like, ooh, his looks really good. Mine's not. Also, I think no, I didn't. Yeah, I don't know what yeah. I'm like, wow, this is really good. Mine's really not. Okay, so I'm gonna multiply this out because this is how I would do it. If I multiply this out, I've got 1/2 times 4 times 3/2 a is gonna be 6a. 3/2 a times 3 over a squared is gonna be 9/2 times 1 over a. And then that times that's gonna be 8a cubed. That times that is gonna be 6a. Okay. Yeah. Which I would then rewrite as 1/2 times 8a cubed plus 6a plus 6a plus 9/2 a to the negative first. Which hopefully, let me just do a quick double check here and make sure it's the same thing he's got. He has got a 16a to the 4th divided by, yeah, 4a, cool, all right. He has got a 12a squared divided by 4a. Oh no, he got 24a squared divided by 4a, which has become 6a cubed, which is, sorry, 6a, yep, cool. And then he's got, that one's the funky one here. He's got a 9/4 divided by a. Yep, we're looking good. We are the same. So you want to make sure, it's a little bit weird. I wouldn't see this a different way personally, but you might. So then taking that function, now we're going to take the derivative of that. For a derivative, derivative of area with respect to little a, which is kind of funky to write, is going to be 1/2 times 24a squared plus 12, and then over here you're going to get minus 9/2 a to the negative second. I'm going to set that equal to 0. Okay, so then what I would do is I would rewrite this as I multiply both sides by 2. So I'm really not worrying about the algebra here. So I'm going to get rid of that by multiplying both sides by 2. I'm going to say 24a squared plus 12 minus 9 over 2a squared equals 0. And then, yeah, I'm not loving this at all. He does something very different. That's fine. Yeah, that's gross. I guess I should, yeah, I'm going to factor out a 1 over a squared, which I was kind of hoping to avoid, but I don't really have a choice here. Yeah, so factoring out the 1 over a squared, I've got 1 over a squared times 24 a to the 4th plus 12a squared minus 9 over 2. Let's factor out a 1/2 as well. No, yeah. So yeah, this is gross. What did I miss? Oh, I see what I missed. I didn't miss something, but like doing it the way I'm doing it is leading me down a path which is not nice. But I also would argue that it's not easy to see exactly what he's done. So I feel like this is where I would probably end up. Yeah. What would I do here? I guess I factor out the 1/2. Yeah, so 1 over 2a squared. And I've got a 48a to the 4th. Okay, I see what I'm going to do. Plus 24a squared minus 9. And I'm going to try and factor this. It's going to be something a squared. I forgot the something there. Times something a squared. Yeah. And then, yeesh. Okay, here's how I think it works out. I'm looking for numbers that multiply. Ooh, yeah, that's gnarly. Oh, I could have factored out a 3. Sorry. Sorry for all the sorries here. This problem's a little bit gnarly. Let's factor out a 3 as well. So I've got 3 over 2a squared times 16a. Oh, this is looking much nicer. 16a to the 4th plus 8a squared minus 3. And then I believe, good God, this is going to factor as, and I think we're going to factor as, yeah, to move it a something a squared, a something a squared. And I think we're going to get, so we need a 3 and a 1. And then I think if I have a 1 that's has to be positive, 1 negative. Let's see, 4. Yeah, I see it. Okay, so you want a -4 and a positive 12. So I want a 4a squared here to give me 4 times 3 is positive 12a squared. And I want a 4 here and a -1 here to give me a -4a squared. And that adds up to positive 8a squared. Gross. This part has no solution because you need the a squared to be negative. This part, you're going to get a squared equal to 1/4, which means a is going to be plus or minus 1/2. But we know that a can't be negative 1/2 because of where this whole function started off. I know it's been a while. If we go back to the picture we started with, we were living over here where a was certainly greater than 0 because that's where the function was defined. So we get a equal to 1/2. We can check to see that minimizes the function, this is where also where things kind of get really gross here. But if I were doing this problem and I knew it was supposed to be a minimum, here's what I would actually do. I wouldn't actually check anything. I would just draw the picture that pretends like I checked everything. Here's my a equal to 1/2. I'm like, yeah, of course I checked it. That the derivative is negative over here. I should really be writing dA dt though, not f prime. dA dA and positive over here, negative positive. Did I check anything? No, I did not check anything. I think you can see though, if I pick a number smaller than 1/2 here, this part is going to be negative, this part's going to be positive. Pick a number bigger than 1/2, this part's going to be positive, this part's going to be positive. So it's not hard to check, but I think you can also get away without checking that if you are smart about it. Yeah, that problem was a little bit gnarly. Okay. So I should go back though and make sure I didn't answer the question fully. Definitely important to check. So wow, yeah, I was ready to be done with that problem. So I'll point out a equals 1/2, which then means that if we look back at what we wrote before, our area, which is what they're asking for. So they could have asked for the dimensions, but they asked for what's the area of the smallest possible triangle. The area is going to be, I'm going to plug that into my area equation, which again, I'll point out is kind of gnarly. My area equation right there. So I'm going to get 1/2. So I'm plugging in. Yeah, sorry. And it's kind of hard to see. I'm just going to write it over here. You guys can kind of see that, I think. Yeah, cool. So I'm going to get area equal to 1/2 times 8 times 1/2 cubed, which is 1/8, plus 12 times 1/2, plus 9/2 times 1/2 to the -1 is 2. This ends up being 1/2 times 1 plus 7 plus 9, which is 1/2 of 16. Sorry. 1 plus. Interesting. He got an area of. He got an area of 8. I clearly made an error somewhere, and it's gonna kill me. I didn't make any other errors though. Oh, how did that 6 become a 7? Good God, I don't know. I think I added 1 plus 6 and got 7 in my head and then wrote down 7. 1 plus 6 plus 9 is 16, and 1/2 of 16 is certainly 8. Cool, great, awesome. Tough problem. All right, let's do the last one here. Provide straightforward and fully justified answers to the following questions. Each of them assume that y equals f of x is continuous. This is 8. So y equals f of x is continuous and I believe differentiable. Prime and double prime, right? F double prime and sorry, f prime and f double prime exist and are continuous. Meaning the function is differentiable or the function is twice differentiable. Sure. So part A, and we did this one in class as well, but good to see again. F of -1 equals 0. And we are given that f prime of x is greater than or equal to 1 for all x. Is it possible that f of 2 is equal to 2? So let's suppose that it is. So suppose f of 2 equals 2. Then by the mean value theorem, between x equals -1 and x equals 2, so right, looking like this, f of -1 is 0, f of 2 is 2. So between those 2 points, there has to exist some other point where the slope of the tangent line is equal to the slope of that secant line connecting those points there. So there must be a number c between -1 and 0, sorry, -1 and 2, apologies, such that f prime of c is equal to the slope of that secant line, which is just f of 2 minus f of -1 over 2 minus -1. F of 2, we're supposing f of 2 is 2. F of 1 we're told is 0. 2 plus 1 is 3, which is 2/3. Can f prime of c equal 2/3? No, not under the assumption that f prime of x is always greater than or equal to 1. This is impossible. Since everything we did was logically plausible from the very beginning, it must follow that our original assumption that f of 2 is equal to 2 is not possible. So we cannot have f of 2 equal to 2. F of 2 would have to be, I think, 3 at the minimum, right? We need f of 2 greater than or equal to 3, so that then this is 3 minus 0 over 3, which is 1, which f prime of x is allowed to be greater than or equal to 1. So let's go to the next part of this question. So same assumptions, but now we're given that f of 0 is equal to 0 and f prime of 0, oh sorry, f of 0 is equal to 1, sorry, f of 0, so let's start this. F prime of 0 is equal to 0 and f of 0 is equal to 1. Is it possible that f has no x-intercept? So can x not have, sorry, can the function not have, geez, can I write the words? Let me just write it. Let's try this again. Sorry. So b, f of 0 equals 1, f prime of 0 equals 0. Can f not have an x-intercept? Now, I want to point out here, it does not say does f have to not have an x-intercept. It's just saying, is it possible? Well, let's think here. So we've got f of 0 equal to 1, and f prime of 0 is equal to 0. So the slope of the tangent line is 0. And if we, so, I mean, yeah, there's lots of functions. Like I can think of, I mean, so I can think of a downward opening parabola, right? I could think of f of x equal to 1 minus x squared. F of 0 equals 1, check. F prime of 0, well, f prime of x is -2x, and f prime of 0 is for sure 0. It is not the function he came up with, but it is a correct answer. So I want to point out for this question, right, you have to really focus on the fact that is it possible that f has no x-intercept? It is certainly I drew one word, sorry, I drew one where it does. Apologies. So that's not the right function. Let's flip it over and say f of x equal to 1 plus x squared. That's what I actually meant to draw. So f of 0 is 1, f prime of x is now still positive 2x. I made a mistake there, sorry. F prime of 0 would be 0. I want to point out that these two examples show two things. This example, the actual right answer shows, yes, it is possible that f of x does not have an x-intercept. But it clearly doesn't have to be true, right? Because you can come up with another function where f of 0 equals 1 and f prime of 0 is still 0, namely this one here, that does have x-intercepts. Yeah, in fact, sorry, I thought he came up with a different function. I was reading it differently. But there are lots of functions that would also work here. Another good example of this would be 1 over 1 plus x squared. That's kind of, f of x equal to 1 over 1 plus x squared. Definitely has no x-intercepts. Certainly does equal 1 when f of 0 is 1. And I will tell you f prime of 0 is equal to 0. Cool. And finally, the last question on this practice test. So again, right, we're assuming the differentiability, the continuity, but we're not assuming anything from part A or B in this next question. So now we are told the following. The only, I would focus on that word, solution to f prime of x equal to 0 is x equal to 2. Moreover, also, f of 2 equals 3. Limit as x goes to negative infinity of f of x is 0. And the limit as x goes to infinity of f of x is equal to 1. Identify the range. Okay, so I would try to graph it. All right, so we know that f of 2 is 3. We also know that's the only place where the derivative is equal to 0. So it's either got to round out like that or round out like that. We know as we go towards infinity, we get closer and closer to 1. I don't love this question. Oh, no, yeah, okay, yeah. Yeah, it's a good question. So we're going to do something like this. And as we go to negative infinity, we get closer and closer to 0. Do something like this. Now you might ask me, James, how do you know you don't go like below the horizontal asymptote here, below the horizontal asymptote here? Well, if I went below the horizontal asymptote, then I would have to turn around and then I'd have a place where the derivative was equal to 0. So the range here has to be as low as almost 0. So we get down to almost 0, as up to as high as that point, which is y equal to 3. And we do get the 3, actually. That's not a bad question. He seems to really like these range questions, I gotta say. So definitely make sure you are cool with range. I'll try to see what I can do about the video quality for this video and the other video. Hopefully I'm able to figure something out. If not, take a look at the notes.